So in this lecture, we will talk about the signal-to-noise ratio penalty of accelerated imaging using sense, and then we'll talk about GRAPPA parallel imaging reconstruction, which is a case-based domain method. Now, there are two mechanisms by which SNR is lost in sense parallel imaging. The first is by reducing the overall time that we're listening to the signal. So that's a reduced scan time, which is equivalent to reducing the amount of averaging that we are doing. And here there's nothing we can do to improve that, except maybe try to make more sensitive receivers with lower noise figures. The other source of SNR loss is ill conditioning of the sense decomposition. That is the inverse problem we have to solve to get back the unaliased pixels. And this, as we'll learn, depends a lot on the coil array geometry and on the scan geometry. So these are factors we can generally control. SNR loss due to poor conditioning of the sense decomposition, this latter term, is quantified as the G factor, which is a function of space, and you're going to be calculating G factor maps for the parallel imaging reconstructions in the homework. Mathematically, the ratio of an accelerated scan, the ratio of the SNR of an accelerated scan to the SNR of a full scan, that's what's written here. So this is the SNR of the accelerated, and this is the SNR of the full, is given by 1 over the G factor, which is again a function of space, times the reduction in scan time factor, which is not a function of space. All right, so this is G factor, and it's a function of space. So that means that overall, this loss in SNR is going to be spatially dependent because of the spatial dependence of G factor. Now, to understand this a bit further, we can note that SNR is equal to the ratio of the signal, the size of the signal, and the square root of the signal's variance. Now, since the signal presumably doesn't change between a fully encoded acquisition and an accelerated one, it must be the variance chi that changes. So for a fully encoded acquisition, last time we learned that the signal variance is equal to 1 over the number of samples. This is a number of K-space locations that we sample, times C sub f complex conjugate psi inverse C sub f inverse, where if you'll recall, the psi sub f, or the psi is the noise covariance matrix across the coils, and the C sub f is a vector of sensitivities at this spatial location. And if we're not doing any acceleration, we don't have any aliasing of any voxels, so each voxel only gets contributions from itself. This was all covered in the previous lecture. This is the variance of one, so this is the variance of one voxel, and it's a scalar. For a reduced acquisition, we have that chi sub r is 1 over n sub k reduced, where this is the number of K-space locations sampled in the accelerated scan, times C sub r complex conjugate psi inverse C sub r inverse. Where again, last time we learned that C sub r is actually a matrix now instead of just a vector, and it's a matrix of sensitivity values collected across all of the voxels that alias onto this location. So the column dimension indexes aliased spatial locations, and the row dimension indexes coils, as before. So this is the covariance matrix then of our aliased voxels. So let's look more specifically at a single voxel here. So the SNR of the reduced acquisition again will be S over square root of chi sub r evaluated at the jth location, right? Because remember chi sub r is a matrix, so if we want the variance, we need to take the jth location, which is on the diagonal of that matrix, and divided by S of square root of chi sub f, the variance of the fully encoded acquisition. Now, of course, the s's cancel out, and we can simplify this to 1 over square root of chi sub r at the jth location divided by chi sub f. And we can then plug in the expression for each of these, and this is equal to 1 over square root of n sub k r, or sorry, n sub k, this is important to get right, n sub k f divided by n sub k r times square root of c sub r, the reduced coil matrix, psi inverse c sub r inverse j at the jth location times the variance of the fully encoded acquisition c sub f, which is a scalar, so it doesn't need an index. Now we can simplify this a bit further then. So now what we do is we generally call this the square root of r, because this n sub kf divided by n sub kr is the amount by which the scan has been reduced, right? That's that factor r. And in this term, the square root of the product of the variances based on the coil sensitivities in the coil noise matrix is called the g factor. So then this simplifies down to 1 over square root of r times g, where g here is the geometry factor, and it's again equal to c sub f transpose psi inverse psi c sub f, another one squeeze in there, times c sub r transpose psi inverse c sub r inverse close bracket jj. And this is called the geometry factor again. It can never be less than 1. By construction, it can never be less than 1. If there's no reduction, if there is no the lowest it can be is if there's no reduction, if there are no aliased pixels in a given location, then this guy simplifies to this guy, and we just have its inverse, right? So it just simplifies to a ratio of 1. Let's see. Now we can equivalently write this for purposes of implementation. It simplifies things a bit if we write it as C transpose psi inverse C jj times C transpose psi inverse C inverse jj. Right, now you only have to build one C matrix, and you take that C matrix to be the reduced C matrix, and then this guy equals the full case for full encoding of pixel j. Now geometry factor is critical for minimizing noise enhancement in parallel imaging, and it depends on several factors which mostly can be controlled. It depends on acceleration, the degree of acceleration. It's a function of spatial location. There are some places where you'll have low G factors and low noise amplification because you don't have a lot of pixels aliasing, or because you have well-separated coil sensitivities in that location. It depends on the aliasing direction. That is the direction in which you're applying the k-space undersampling. And in particular, it depends on where that's happening with respect to the coil geometry. It's generally a good idea to align the dimension along which you have lots of variation in your coil sensitivities with the direction where you're doing the undersampling. So minimizing the G factor, or making it as spatially uniform as possible, drives system design, and especially the coil design. And sense coils then are really different from traditional array coils, that is, coils that are well suited for getting really high SNR sum of squares reconstruction. For these kinds of coils, we'd like to have many observations of the same tissue from multiple views, multiple coils. Whereas for sense coils, what we principally care about is that each spatial location really has a single coil dominating. Okay, so here's an example of a good sense coil in 1D. So let's consider this case where we have two coils, C1 and C2, and we're going to accelerate by a factor of 2 and have two spatial locations then aliasing on top of each other. Okay, so at x1, at spatial location x1, we have that the coil vector is 1 and 0.3. Okay, so that's this location, and so this guy is C2 of x, and this guy is C1 of x. So at this spatial location, x1, C2 is small, that's 0.3, and C1 is large, near 1. Okay? And conversely, what we're going to say, just by construction here, is that voxels x1 and x2 alias on top of each other, and by construction also, the coils have opposite sensitivities at those two spatial locations. Okay, so x2 in the reconstructed image is going to alias on top of x1. We're going to have to separate them back out in the sense reconstruction. And at x2, coil 2 is high and coil 1 is low, and it contrasts with x1 where coil 1 is high and coil 2 is low. Okay, so let's assume that we have a perfect coil noise matrix. So it's an identity matrix. That gives us a G factor of square root of C sub F transpose times C sub F times C sub R transpose, no noise correlation matrix in there since it's identity, inverse JJ. Okay? Sorry, not JJ. We want it to be 1, 1. Right? This is at spatial location x1. So we can then plug in our sensitivity values into the G factor equation and evaluate everything. For the CF transpose CF term, we get that the product of these two sensitivity vectors, and this is only considering spatial location x1, is 1.09. That then gives us a chi sub f, a noise variance for the fully sampled acquisition of 1 over the number of k-space samples for the fully sampled acquisition times 0.91. Likewise, we can multiply CR transpose in CR. And this is now a matrix, right? 2 by 2 matrix multiplied by itself also gives you a 2 by 2 matrix. Note that this term here is equal to this term, like the first entry is the same in both of them. But in the G factor equation, we have to invert this guy and then take the first entry. So we invert this, we get this equation, which you can also do analytically. And then we get, when we plug the first entry here and the first entry here and this guy in to the G factor equation, we get square root of 1.09 times 1.316. And that gives us 1.20 overall, or a 20% loss in SNR due to geometry factor. So this 1.09 here can also be interpreted as the loss due to using multiple coils to observe this spatial location, and then the condition loss is the 1.316. That is a measure of the conditioning of the inverse C transpose CR matrix. Okay, so then overall the SNR, the ratio of the accelerated SNR to the full SNR is 1 over root 2 times 1.20. Right, we get root 2 again because we're accelerating by a factor of 2. We have 2 aliased voxels here, and that gives us 0.59, or a 40% SNR loss, which is pretty significant. But this is still overall a good sense coil. Okay, so compared to that, in a case of an example of a good array coil, where again here the design objective is to get sensitivity everywhere with multiple coils. Okay, so this now will be still c sub 2 of x, and this guy will be c sub 1 of x. But now instead of one of them being high and the other one being way depressed down to 0.3, what we would really like to have is that they're both kind of high everywhere. Okay, so then if we look at what we've got here, we've got that c1 of x1 is 1, c2 of x1 is 0.7, and vice versa for voxel x2. Okay, so at spatial location x1, c sub f is 1 and 0.7. And if we accelerate this by a factor of 2, we get 1, 0.7, 0.71 for our CR matrix. That's the values of the sensitivities at x2 concatenated to the values of the sensitivities at x1, where these are the two voxels that are going to alias on top of each other if we accelerate by a factor of 2. So next what we're going to do is we're going to calculate both the fully sampled SNR as we did in this case, right? Because that is what we are trying to maximize if we're using like an array coil and no parallel imaging acceleration. Whereas G factor is what we're trying to minimize. Sorry, we're trying to minimize the noise variance in this case, right? We care about the noise variance of the fully sampled acquisition in this case, and we care less about the G factor, right? So here we designed a coil that gave us overall lower G factor here. And what we're going to see with this one is that we're going to get an improved value for the fully sampled case, but a worse value for the G factor, because we have now tried to design a coil that is better as an array coil where we have more sensitivity everywhere from every element, versus a sense coil where we have more sharply defined coil sensitivities that are better localized. Now here, our CF transpose CF is going to be a much larger value than it was for the good sense coil, and that's going to lead to a noise standard variance for the fully sampled acquisition, again of 1 over n sub kf. This is going to be the same in both cases, but it's going to be multiplied by now 1 over 1.49, which is about 0.67. So this is a lower number than it was for the sense case. So that number has improved. However, when we multiply CR transpose CR, we get this matrix, and if we then invert that, we get much larger values in the inverse. So when we plug in the first element of the CR transpose CR inverse matrix here, and the first element and this element here as the fully sampled guy, then we get a G factor that is much higher, or 2.92, corresponding to 3 times lower SNR. Compared to the fully sampled acquisition, and it's considerably worse than the good sense coil case. Okay, so then if we take the ratio of the accelerated scans SNR to the fully sampled scan SNR, then we have 1 over root 2, which is the scan acceleration factor, and also multiplied by 2.92, which gives overall a factor of 0.24, or 4 times lower SNR / 75% SNR loss compared to the fully sampled acquisition. So here we have, here what I've done is shown 2 different coils, one that's very good for sense, which has a little bit higher noise if it's used just as an array coil in a fully sampled acquisition, but has much better G factor, and compared to a good array coil, which every coil has a lot of sensitivity everywhere, and that gives us a better SNR in the fully sampled case, but a much worse SNR if we decide to accelerate the scan. Okay, so to summarize, sense coils should be designed for very local sensitivities, right? They should fall off rapidly. Their sensitivities should fall off rapidly as you move away from the coil. They should be as orthogonal as possible. The sensitivities should be as orthogonal as possible. Ideally, the inner products of the coil sensitivities would be 0. And they should be designed to optimize SNR in the reconstruction. Okay, so you can directly come up with a coil design, and if you have a specific sense accelerated acquisition in mind where you want to use that coil, you can calculate its sensitivities or measure them in the MR scanner and look at how good it's going to be for that specific scan. So a lot of work has gone into optimizing coils then to get low G factors for modern, especially modern neuroimaging. Conversely, array coils should be designed for larger sensitivities that don't fall off so far away, that don't fall off quickly as you move away from the coil. So there's larger sensitivities, or larger sensitive volumes. And then they ideally would give you also approximately uniform signal intensity if you do a root sum of squares reconstruction. Okay, you'd like to not have a lot of shading left over if you ignore the sensitivities in a root sum of squares reconstruction. So that concludes our discussion of sense parallel imaging reconstruction. Now let's talk about the main alternative to that, which is called GRAPPA, and it's a frequency domain parallel imaging reconstruction. Okay, so in GRAPPA, we actually transform everything to K-space. So in the image domain, as we've shown before, we have a coil that's sitting next to the body, and that coil has a receive sensitivity associated with it. And in the image domain, the signal that we get from that coil, or the image that we would get from that coil, is equal to the underlying signal from the body times that coil sensitivity. Of course, we can transfer everything to K-space, and there the signal from the body will convolve with the Fourier transform of the sensitivity. Right? So now we have functions of k for each of them, because a multiplication in one domain is a convolution in the other domain. So here I've illustrated a Cartesian acquisition that is well suited for GRAPPA reconstruction. Here the delta k here is 1 over the field of view. And what we are doing, what I'm illustrating here, is that we can think of this convolution as being like a weighted average of the signal around each coil's sensitivity, around each sample that we collect, where that convolution, where the signal that you get is a sum of weighted K-space data, where the weights are given by the Fourier transform of the coil sensitivity. So here, what I've drawn is the Fourier transform of the sensitivity, which, because it's slowly varying in space, right, because C sub j, the coil sensitivities, are smooth functions of space, that means they are compact in the frequency domain. So as we move along in K-space and move to in sample data at each K-space location, what we actually get from each coil is a weighted average of all the K-space data around it, where the weights are given by that coil's sensitivity. And it's a local effect, right? We're not going to get signal in this spatial location. We're still not going to get signal from way down here because the sensitivities are compact, just like they were when we were doing gridded reconstruction. Okay, so coil sensitivities are local in local in image space, and extended a bit then in K-space. Right? They are smooth, but they're still somewhat localized, right? Which means that when we take their Fourier transform compared to a uniform sensitivity, we will get some blurring. They'll be extended a little bit out in K-space, not very far, but a little bit. So each coil then measures a weighted average of K-space data in a neighborhood around each visited K-space location. Sorry, that says weighted average. Each coil measures a weighted average of data in a neighborhood around each visited K-space location. And because each coil sensitivity is different, both in the space and the Fourier domain, each coil's weights are different. So this is a clue about how we might be able to fill in data that we miss. Okay, so what I'm showing here then is, in this acquisition, the solid lines represent data that we did collect, and the dashed lines represent data that we did not collect but need to fill back in. And so what one does in a GRAPPA reconstruction is you take the data that you did collect and you multiply it by a certain set of weights that synthesize the data in between, right? So you take data from this line and multiply it by a set of weights that we have yet to discuss how to determine, and that synthesizes the data in between those nearby lines. And those weights are going to be based on the Fourier transforms of the coil sensitivities. Okay, so in order to get the data back, we need some proper weights that we can apply to the acquired data to synthesize the data in between the acquired data. Or stated another way, we want to find a set of coefficients, and we're going to call these coefficients a sub I, j, k, where I and j index k-space locations, and k indexes coils. Okay, and we want to find a set of coefficients a, I, j, k such that we can fill in data for each coil. So this is what we're going to define as the missing data for coil L as m hat sub L of kx, ky. And we're going to try to find a set of coefficients such that the following expression is satisfied. That the sum over nearby spatial locations, or k-space locations, I, j, right? I is going to index, for example, over readout points, and k will, and j will index over nearby phase encoding lines, and then k will further index across different coils. So we're going to take every coil's data and use it to synthesize every coil's missing data. Okay, we're gonna try to figure out what the coefficients are to satisfy this expression: a sub I j k times m sub k of kx plus I delta k, comma ky plus j delta k. So these are the weights, and this m sub k is the data in the neighborhood around kx, ky. And I and j index acquired samples in the neighborhood around this point kx, ky, that where that point kx, ky needs to have data synthesized for it, right? So let me say this one more time because it's important to get this right. What we're saying is that we want to find a set of weights such that when we multiply those weights by the data around a given k-space location kx, ky, right, and where those points are indexed by I and j, and we're also going to sum across all the coils k, right? So we're going to have different k-space data for every coil and also different weights for every coil. When we multiply these weights by that data, we should get the data back for this coil L, okay? Where again, I sub j index acquired samples in the neighborhood around the point kx, ky, where this is the point that we're trying to synthesize. And so here's an illustration of this. So in the middle here is the location kx, ky that we're trying to synthesize. So this is the m hat sub L of kx, ky. And we are going to use all that coil's data and all the other coil's data and weight that data to try to synthesize this point. Okay? So what we would do is we would take this coil's data at this offset, which would be A111, because this is coil 1. So this is coil 1, that's the last index, and then this is one offset in kx and one offset in ky. So we're going to multiply this data point by A111 to try to get this, and we're going to sum it with all the other weighted data points, where, for example, the data in coil L will be multiplied by A11L, and the data on the opposite side of this line from the to be synthesized point is going to see a weight of A1 minus 1 comma L. Right, so we're going to have all these weights, we're going to multiply by all the data, and the sum of all that weighted data is going to give us the missing k-space data point. So there's one coefficient for each neighborhood sample for each coil that we're going to apply to try to get the data, to synthesize the data back for each coil. Now this seems like a lot of bookkeeping and a lot of coefficients, but the thing to note is that the same coefficients work everywhere in k-space. So all you have to do is slide the neighborhood to be centered on, so that it's centered on each unacquired data point, and then fill in that unacquired data point coil by coil, line by line, point by point. Okay? And then the neighborhood of coefficients is called the Grappa operator, or that is like the collection of the I, J, K The collection of those coefficients is called the Grappa operator. And then once you're done with this procedure, what you have is a full set of k-space data for every coil, right? And so once the data is filled in, you still need to combine those coil images. So you reconstruct each coil's image by 2D-FT, right? We have k-space data, so we first need to take the 2D Fourier transform. And then we need to combine the coil images either using a sum of squares reconstruction, which we talked about previously, or a multi-coil reconstruction, which we've also talked about previously, which can then use sensitivities. So next time we will expand further on the Grappa reconstruction by talking about how to find specifically these coefficients AI, J, K that make up the Grappa operator.